In this video, we will be tackling a fascinating optimization problem that combines both geometry and calculus. We will take an equilateral triangle, and within this triangle, we're going to inscribe a rectangle with one side resting along the base of the triangle. The question we will be looking at is, what is the largest possible area that this rectangle can achieve? We'll start by setting up a function that represents the area of our rectangle in terms of variables x and y. We'll then solve for y in terms of x, and then we'll use calculus to find the maximum area by taking the derivative of our area function. To start, let's set up our equilateral triangle with side length L. Our goal is to create a function that expresses the area of a rectangle inscribed in this triangle, or one side of the rectangle lies along the base of the triangle. First, we'll split the equilateral triangle into two right triangles by drawing an altitude from the top vertex to the midpoint of the base. Each right triangle now has a base of 1/2 L, a height of square root of 3 over 2L, and a hypotenuse of L. Now, let's focus on one of these right triangles for a moment. We'll denote y as the height of our rectangle and x as the length of the rectangle's base within this right triangle. We will note that there is a right triangle formed by drawing an altitude from y to the base. We will denote the base of this triangle with the value of x sub 1. By using the similarity of triangles, we can relate y and x1 to values in terms of L. The ratio of heights to the bases in similar triangles gives us the following. Y over x1 equals square root of 3 over 2L divided by 1/2 L, which simplifies to y over x1 equals square root of 3, and we can solve for y to get y equals square root of 3 x1. Next, the total length of the base of our original right triangle is x plus x1, where x1 is the base of our smaller, similar right triangle. Since the full base of our big right triangle is 1/2 L, we get the following. X plus x1 equals 1/2 L. Solving for x1, we get that x1 equals 1/2 L minus x. Substituting this into our earlier equation for y, we get y equals the square root of 3 times 1/2 L minus x. With y expressed in terms of x, we can now write the area of the rectangle. The area A is given by the following. A equals 2 times x times y. This is because our equilateral triangle was split into two right triangles, and we just solved for the area of the rectangle inscribed in one of our right triangles. To get the area in our full triangle, we have to double it. Substituting y into this formula, we have area equals 2x times the square root of 3 times 1/2 L minus x. And there we have our area function in terms of just x. Now we can proceed to find the maximum area using calculus. To find the maximum area of our rectangle, we need to analyze our area function using calculus. Our area function is denoted by a equals 2 square root of 3 times x times 1/2 L minus x. Let's simplify and differentiate this function to find the critical points. First, let's distribute x within the parentheses to get a equals 2 square root of 3 times 1/2 Lx minus x squared. Now, we'll distribute the 2 square root of 3 to get a equals square root of 3 Lx minus 2 square root of 3x squared. To find the critical points, we will differentiate a with respect to x and get dA dx equals square root of 3L minus 4 square root of 3x. Now, to solve for the critical points, we'll set the derivative equal to 0, which will give us square root of 3l minus 4 square root of 3x equals 0. Solving for x, we get that x equals L over 4. Next, we need to confirm that this critical point gives us a maximum. Since the area function is a downward-facing parabola, indicated by the negative coefficient in front of x squared, the critical point x equals L over 4 is a maximum. To find the maximum area, we will substitute x equals L over 4 back into our area function to get a equals 2 square root of 3 times L over 4 times 1/2 L minus L over 4. Simplifying the parentheses, we get 1/2 L minus L over 4 is just equal to L over 4. So our area max is equal to 2 square root of 3 times L over 4 times L over 4, which simplifies down to 2 square root of 3 times L squared over 16, which simplifies to square root of 3 over 8 times L squared. So the maximum area of the inscribed rectangle is square root of 3 over 8L squared. In summary, when the rectangle's base is L over 2 and its height is square root of 3 over 4L, we achieve this maximum area. And there you have it. We've explored how to find the largest rectangle that can be inscribed in an equilateral triangle with one side of the rectangle lying on the base. By setting up our area function and applying calculus, we determined that the maximum area of the rectangle is square root of 3 over 8L squared. To recap what we did, we derived our area function by analyzing the relationships within the right triangles formed by splitting the equilateral triangle in half. We then used differentiation to find critical points and verified that the maximum area is achieved when the rectangle's base is L over 2 and its height is square root of 3 over 4L. I hope you enjoyed this mathematical journey. Thanks for watching, and I'll see you in the next one.